Hello, everyone, and welcome to the Collaborative Science for Estuaries webinar series. This is Nick Sobral with the Science Collaborative, joined remotely by Megan Brass. Thank you for joining us for this month's webinar on sediment dynamics, featuring the absolutely phenomenal work of a 3-year collaborative research project on Oregon's Coos Estuary. And before we get started with the presentation, I'll give a quick bit of background on our program and the reserve system that we work with. So the National Estuarine Research Reserve System is a national network of unique research reserves as shown on this map. This is a NOAA program that works in collaboration with a local place-based partner, either state agency, university, or nonprofit. Each reserve site includes programs focused on land stewardship, research, and scientific monitoring, training programs for the public and local officials, and education. The Science Collaborative supports science for estuarine and coastal decision makers by coordinating regular funding opportunities and supporting user-driven collaborative research, assessment, and transfer activities that address critical coastal management needs identified by the reserves. The webinar series features project teams supported by the Science Collaborative, program staff, and partners. Speakers share their unique approaches to addressing current coastal and estuarine management issues. And if that sounds interesting to you, join us for future webinars to learn about new methods to integrate technical experts and users of project outputs into the research process and how their research results and products might inform your work. A little bit of housekeeping here. All attendees are muted upon entry. So we'll be handling the Q&A via GoToWebinar's questions feature, which you can find on your console there. You can enter questions for the presenters as they occur to you throughout the webinar. In fact, we encourage it so you don't forget them. And using the Q&A feature, and we'll discuss as many as we can during the final portion of today's webinar after the presentation part itself. And the chat is only visible to organizers, so you can also use it to alert us if you have any sort of technical issues on your end. And with that, I will introduce our speakers for today's session. We are thrilled to have 3 members of one of our collaborative research project teams presenting today. We'll start with a presentation from David Sutherland, Emily Eidam, and Jenni Schmitt, leaving some time at the end for Q&A with the presenters. And David Ralston from the Woods Hole Oceanographic Institution was kind enough to also participate as a panelist for the Q&A. So thank you to all of you. David Sutherland is a coastal physical oceanographer at the University of Oregon, studying estuarine dynamics in Oregon, as well as glacial fjords in Alaska and Greenland. And for this project, Dave served as both the project and collaborative lead, coordinating the many aspects of the project and end user engagement. He also co-led the technical elements, including the fieldwork and model development. Emily Eidam is a fluvial and coastal sedimentologist at University of North Carolina, studying sediment transport and accumulation in diverse environments, primarily in the Arctic. And Emily began the project as a postdoctoral scholar, contributing significantly to the model development, and then transitioned to a co-PI role when she moved to UNC. And Jenni Schmitt is the watershed monitoring coordinator at the South Slough National Estuarine Research Reserve. Her research interests include understanding wetland ecosystems with a focus on how climate change influences habitats and species. Jenni also organizes and chairs the Partnership for Coastal Watersheds, a collaborative stakeholder group whose members are currently working to guide improved estuary management by using tools such as the hydrodynamic model. And that's a lot of talking for me, so I'm going to pass it to Dave now to take over the presentation.
All right, thank you, Nick. I'm gonna switch slides here to our title slide, and while it's switching here, there we go. I want to take this opportunity also to thank Megan Brass, who's on the line as well, and the whole NERRS Science Collaborative group. Obviously, we couldn't have done this project without their really significant funding and support, and all those quarterly calls we had with the program manager team kept us on track. So thank you for that. So Nick gave a brief introduction to the project and to the 3 of us who are presenting today, but there are a whole host of other people that were involved. And what you're seeing here is a picture of Marshfield Channel, which is part of the Coos Estuary. But I want to particularly thank Ali Helms, also from South Slough NERR, Dave Ralston from Woods Hole, Peter Ruggiero from Oregon State, Friedland Reeser from Coos Watershed. Those were all co-PIs on this project. And then we have some other folks from the University of Oregon who helped extensively, particularly Bass Dye and Ted Conroy in the model development that we'll talk about today. All right, so I'm going to pass the mic now after that brief introduction to Jenni Schmitt, who's going to set the stage for us here. So Jenni, it's all yours.
All right. Thanks, Dave. So I'm just going to start by giving you all a quick intro to South Slough, including its geographical context, and then move into how this project got started. So the South Slough National Estuarine Research Reserve is in Oregon, and it's one of the 29 national estuarine research reserves around the nation. And the mission of the South Slough Reserve is to improve understanding and stewardship of Pacific Northwest estuaries and coastal watersheds. The South Slough Estuary itself is situated on the south coast of Oregon, and it's one of the major estuarine arms of the greater Coos Estuary. The Coos is the 6th largest estuary on the west coast and the largest on the coast of Oregon, and it's characterized as a drowned river mouth estuary. It's also home to the largest and commercially most important shipping port on the Oregon coast, yet it also hosts abundant and diverse estuarine habitats. And it's this combination of like a wealth of natural resources with a deep draft estuary and industry surrounding that has led to really important regional industries like the timber industry, crabbing, aquaculture, and commercial fishing. In addition to these industries, the estuary also supports an array of recreational activities. So you see a lot of recreational fishing and clamming and kayaking, for example. And the estuary and surrounding watershed is also the historic homeland of 3 federally recognized tribes. So there's different management objectives for economic development interests, natural resource protection organizations, tribes, and promoters of community and social well-being. And these interests can sometimes be at odds with one another. So in 2010, a collaborative group called the Partnership for Coastal Watersheds was formed. This group is composed of county and city planners, natural resource managers, tribal representatives, development and conservation interests, so a whole suite of different interest groups. And the goal is really to work together to understand local watershed conditions and address the Coos Estuary's capacity and resiliency to serve the economic, the ecological, and the social needs for present and future generations. So it was conversations by this stakeholder group, the Partnership for Coastal Watersheds, along with some other government agencies that really identified a common and crucial need to fill some data gaps in order for a variety of these interest groups to be able to address their various management objectives for the Coos Estuary, whatever those objectives were. So the goal of this particular project was to provide a more solid scientific understanding of the Coos Estuary for these various interest groups. So this included creating and validating a 3-dimensional hydrodynamic model, characterizing estuary circulation patterns over seasonal cycles, identifying present-day sediment distribution, and predicting how sediment deposition and accretion might change from both natural and human-induced causes. And there were really some specific cases of interest to stakeholders. One of those included understanding the effects of a proposed dredging scenario that was put forth to deepen and widen the Coos Estuary's main shipping channel. But there was also basic knowledge gaps that our stakeholders agreed needed to be filled, such as characterizing just the basic estuarine bathymetry for the estuary and understanding what accretion and erosion patterns were. So I guess now I'm going to hand it off to Dave, and he'll start filling in the details of this project so that you can see how what really began as a conversation among stakeholders turned into a really amazing project that responded to the needs of those stakeholders. So you're up, Dave.
All right, thank you, Jenny. Yeah, I think one of the main reasons you'll see along the way that this project was successful was that it came about because of that interaction with the stakeholder group and with Jenny and the team at South Slough. So today we're going to give you a few of the project highlights, and that includes talking a little bit about that hydrodynamic and sediment model that we developed for Coos Bay and what sort of applied questions we answered with it, particularly how we use that model to explore the estuary change over the past 150 years. So we're going back to what the estuary used to look like. So the Coos Estuary has been heavily modified from its natural state, and then thinking about maybe what it's going to look like in the future if, under some proposed dredging and channel widening scenarios. And then, some other highlights are this further collaboration we've had with Jenni's Partnership for Coastal Watersheds group, as well as other end users and stakeholders who aren't necessarily officially part of that group. And of course, it inspired, like all projects normally do, it inspired a lot of questions that we couldn't answer, and that led to a new science collaborative project that we have embarked on just this past year. And I'll mention right here that there is a project page for this that has all the scientific papers that have come out of it. There's data products, there's some movies, there's YouTube movies. There's a whole host of things that you can find if you go to that link below. And I think Megan actually posted it in the chat. So thank you, Megan. All right, so some of you might be familiar with what it takes to build a hydrodynamic simulation of an estuary if you're trying to understand the estuarine circulation, especially in a 3D sense. How does salt move in and out of the estuary? How do the tides propagate? All of that is needed if you want to understand, the add-on things like sediment or nutrients or the biology that is important in the estuary. And the first thing you need for any estuarine dynamics question to understand an estuary is an understanding of the bathymetry. So this is just a picture of Coos Bay from Google Earth, and you can certainly get an idea of the estuarine geometry from a picture like this, but you don't necessarily know the bathymetry, which is really important. And obviously, there's maps, so you can look at a NOAA chart of Coos Bay, which I'm showing here. I think this is a 2011 map, I don't expect you to see the numbers here, but there's numbers all in the channel, the main channel. You can see that it's deeper, it's this white portion. But there's a lot of space in the estuary that has no numbers, has no soundings. And when we started out this project, we realized very quickly that to understand the areas of the estuary that people are really concerned about, or where sediment erosion or accretion hotspots are going to be in these areas that aren't maybe necessarily in the main channel where we have good bathymetry. So one of our first goals and one of our first activities was to develop the best bathymetric product we come up with. And it's actually a little bit challenging in really shallow estuaries. So one of our co-PIs, Peter Ruggiero, most of the reason he was on the project was to collect this bathymetric data, and he does it with single beam echo sounder instrumented jet skis. And so they kind of mow the lawn of the estuary with these jet skis, and I pictured the two jet skis here. And with jet skis, you can get really shallow water bathymetry. And luckily, Coos Bay, well, this is a picture of the transects that they collected. So in red, this is from basically a few days worth of jet ski transects. Are the red straight lines back and forth. So they follow like a predetermined GPS line to collect the bathymetry. And you can see the planned transects in blue. The other really nice thing about doing this bathymetric data collection via jet ski is that every once in a while, they could actually take a sediment grab sample of the seafloor while they were doing the bathymetric data collection. And those are marked by the stars in this plot. And when Emily talks a little bit later about the sediment dynamics in the estuary, to initialize and to think about how sediment moves through the estuary, you actually have to know what sediment's there to begin with. And so these data were really important to that initialization of the sediment dynamics model. So again, what you can also tell maybe by this plot is that the jet ski data doesn't cover everywhere on the estuary. So we actually were able to take Peter's data from the jet skis and combine it with some other sources of data. And I'll show you those now. And Coos Bay is, we feel pretty lucky that there are a lot of data sources in Coos Bay, not just for bathymetry, but you'll see later on that there's, with the South Slough National Estuarine Reserve there, and with the tribes, and with some Oregon state agencies, there's a lot of data being collected in Coos Bay. And so to build this bathymetric database, we actually were able to combine a coastal LIDAR data set that was collected by the Army Corps, and that's shown in the background in gray. And it had some data gaps, in particular where the water was very turbid, but in some places it could actually see through the water to the seafloor. Then the orange is the single beam data that we got from this project from the jet skis. And then the green lines show some Oregon Department of Fish and Wildlife single beam data that they collect for shellfish and clamming studies, habitat studies. And then the Army Corps actually does surveys that are shown in light blue because they dredge the main channel every year. So they usually end up doing a lot of hydrographic and bathymetric surveys. So we were able to combine all these data into a really nice data set at 2-meter horizontal resolution. And that's what's shown here in the color. And the numbers here represent kilometers from the estuary mouth. So you can see that the estuary is about 25 kilometers long if you go up the main channel up to the Coos River, which is the main source of fresh water to the estuary. You can also see that, we'll talk about it later on, but the pink dashed line is a proposed scenario for a widening and deepening of the channel in Coos Bay, and we explore the effects of that on the estuary. But this final project was actually the most widely shared deliverable that, well, it still is the most widely shared deliverable that we have from this project. We were surprised by how widely it got distributed and how many different groups ended up wanting it. I think we're up to 15 to 20 different groups around Oregon that have asked for it and used it, and it's available online for free. So, you know, sometimes those most mundane things are the most useful. But, you know, from the modeling point of view, we wanted to go beyond the bathymetry actually, right? This was supposed to be the year one activity to get us into actually building the simulations. So when I say model, I actually mean the simulations, if you're not used to that word, model. And I'm just showing you now, you know, we take that bathymetric product and we build a model grid. And so the model is called FBCOM, and it's built on this unstructured triangular element grid. And you can see, this is just a zoom in of the estuary mouth, and you can actually see the individual elements here inside the mouth. The resolution is about 15 meters. And this is just the main channel up around North Bend and into the East Bay flats, again, showing the model grid and the model grid resolution that we interpolate the bathymetry onto. And that's really essential to getting these realistic simulations, right? So we're not doing idealized theoretical simulations. We were actually trying to, you know, do a hindcast simulation of a certain year so that we could actually make sure that the model is doing something reasonable. It's really easy to build a model. It's harder to build a model that maybe resembles reality, and that's what you want. And so getting the right bathymetry and then having observations to be able to validate the model, those are two really important ingredients. And in Coos Bay, we were lucky to have both those ingredients. And it was a big effort by a past master's student of mine, Ted Conroy, and then Bass Dye to get this realistic model up and running. But we were successful. And just to show you what the model looks like, here's a brief, you know, a few tidal cycles of surface salinity in the model. So blues here are fresh, red is saltier, and you're seeing, so what you're seeing is basically the pulsing of the tide in and out, and you can see as on the ebb tide, it pushes fresh water out of the estuary mouth, sucks in salty water on the flood. And then you can also see that the model includes wetting and drying, which is really important for this estuary because the tidal flats are extensive. And if you don't capture that, then you're missing a whole really big part of the estuarine dynamics. But you can also see where the fresh water is coming in through the Coos River here. And then we have about 12 or 13 other nodes of freshwater input, but they're fairly small compared to the Coos River. And then South Slough is down here, the southern arm, fairly close to the estuary mouth. So this is just one snippet of the model, but I can point you to the project papers if you're more interested in how we did it and how we validated the model. But for the purpose of this talk, you know, we have now this well-validated hydrodynamic model. So it's the physics, we have the circulation, and on top of that, now we're going to add the sediment dynamics. You know, the basis of the sediment dynamics model is the physics model, the hydrodynamic model that we had. But to get it initialized, like I mentioned before, you need to have some observations. And that's what's being shown here is grain size observations. The circles are the observations, and the background is the sediment bed grain size from the model itself. And if you sort of glaze your eyes and look at it, it does a pretty good job at the big picture characterization of the sediment bed in the estuary. And one of the big, so just to show you how sediment moves to the estuary, I think Emily wanted us to focus here on the middle right panel. So if you look at this middle right panel, what it's showing is depth average suspended sediment concentrations. And so red is higher, blues are low sediment concentrations, right? So most of the sediment is coming out through the river, and then it gets either deposited somewhere in the bed. That sediment can also get resuspended and exported out of the estuary. And what I want you to look at in the right-hand side, this is the present day case. I'll talk about the historic case, which is on the left side in a little bit. But what we're going through here is a river discharge event. So here's river discharge. You can see it spikes here, and then several tidal flats. But you can see the main routing of the sediment in the present day case is actually through the main channel of the estuary. And that sediment seems to increase as you go up estuary. And then some sediment is actually being pumped up into one of these sloughs. This is Isthmus Slough that actually has no real river connection coming into it. And so that's sort of how the present day sediment dynamics work. And we're going to contrast that with what was happening in the past, and then maybe what will happen in the future. So to sort of set the stage for why we're considering the past here, I think it's important to remember that Coos Bay didn't always look the way that it did. This is a map, an 1895 map from NOAA that we got from some archives at the University of Oregon Library. And you can tell right away that the estuary actually looked fairly different, right? There was no jetties at the estuary mouth. There was no Charleston. There's no Charleston Harbor. Marshfield Channel was not maybe the main channel that the Coos River actually exited into. The airport wasn't there. So all these different changes that I'll highlight in a little bit. So this was, in 1895, the estuary was much, it was still actually already pretty well used, but it was in a more natural state. And the picture in the upper left is actually showing them constructing the jetty. And so they actually built a train track out into the ocean to deposit the rocks and build the jetty at the estuary mouth. So you compare that to again, this present day map. This is a 2011 map that I showed you earlier. You can, I'm going to show you a more specific plot next, I think, to highlight the differences, but you should be able to see some differences right away. So I will mention too that what we did is actually we have the sort of the 1895 map, and then in this colored legend down here, these are the other maps that we were able to find. So we had maps from 1895 all the way up to 2011, from 1912, 1927, 1940. So we were able to look at sort of the change in the estuarine area and volume over time. And this was a lot of work, a lot of hand digitization that was done by an undergrad at UO, Kira Bartlett. So thanks to Kira for that, and to Emily for advising her. But what I'm showing you here is the 1895 area, which is the background map. And then the purple outline is what the estuary looks like now. And you can see a few things. You can see the airport, and that's shown in this bottom middle plot here as well. You can also see dredge spoil islands that were built as they started dredging the main channel. So these islands in the East Bay are actually artificial human-made islands. You can also see sort of the rerouting of Marshfield Channel, which is where the Coos River exits into. So instead of having this channel alongside the estuary being the main conduit for fresh water from the Coos, Marshfield Channel was sort of created, and you'll see later on that became sort of the main conduit for sediment as well. And then Charleston Harbor, the last main difference was Charleston Harbor was built out here, and the jetties were built, and then the main channel was dredged out. And I see Emily is back. It's very exciting. Welcome back, Emily. So I was just walking people through the changes to the estuarine shoreline. I haven't talked specifically about the changes to the area or the volume yet. I don't know if you want to take it over from here, but.
Sure, I'd be happy to. Thanks for stepping in. I apologize for our brief internet outage. We've had some interesting internet connectivity today.
No
All
worries.
right, so I'll pick up from here. One of the things that we were interested to think about as we were doing this shoreline mapping and looking at all the new bathymetry we collected was how has the overall geometry of the estuary changed? And interestingly, a lot of the reclamation that happened in the form of the creation of these dredge spoil islands and expansion of shorelines decreased the total area of the estuary, and that's what this plot shows going back in time to 1860s when we have some of those early maps. But what's interesting is that that decrease in estuarine area actually occurred together with an increase in the overall volume. So we filled in a lot of the shallow areas, but we also dredged out a deep navigation channel. So that led to sort of this shift in the overall estuary having a greater percentage of deep areas, but overall less area. And that's actually not uncommon for a lot of estuaries in the US. They were developed in order to allow larger ships to come through, but we also needed more port areas to facilitate those ships, so we filled in shallow areas. So we were interested to go in and see if we could evaluate those effects of decreasing area and increasing volume on the hydrodynamics, so the flow of water through the estuary, as well as the sediment dynamics. So we took the digitized historic maps and we recreated the model, a bathymetric grid for the model for the historic mid to late 1800s case. And we reran the model on that, and then we had already been running the model on the present day case. And then we also recreated the grid again to reflect the proposed channel deepening on the west side for the deep draft development project. So I'll focus in on some of the results, some of the changes that we saw between the historic and modern case, and I'll just note that the trends that we saw in sediment dynamics between historic and modern were basically perpetuated through the proposed case. They were just amplified a little bit more between the modern and the proposed. So this is a figure that highlights one of the properties we were looking at, and Dave showed you the model of the overall flow of sediment that we're able to model through the estuary. And this is one of the main takeaways. On the left, we're showing the historic estuarine case, and this is a map of the depth integrated suspended sediment. So basically how muddy the water is in different parts of the estuary. And then on the right, we have the present day case. And this is a snapshot from a simulated high river discharge event. So if you imagine a winter rainstorm that flushes sediment off the hills and the landscapes nearby and carries it into the estuary. On the left-hand side, you'll see this big red hotspot on those shallow intertidal flats on the east side of the bay. In the historic case, when the river discharged naturally to sort of this broad network of shallow distributary channels on top of the intertidal flats, a lot of that sediment was able to be broadly dispersed throughout those tidal flats. In the present day case on the right, that channel has been dredged out and the river is now much better connected to the main navigation channel left. So now a lot of the sediment delivered by the Coos River, the main source of sediment to the estuary, really bypasses these intertidal flats to a large extent. Some of the sediment still makes it onto those flats, but a lot of it gets very directly funneled down Marshfield Channel and into this now deeper navigation channel. So that has resulted in actually an overall decrease in turbidity on those intertidal flats for those high discharge events. We also note that in terms of the vertical structure of what's happening in the estuary, the deepening of this navigation channel means that we now have much greater salt propagation up the estuary. And in these two plots, we're showing colors that show the amount of suspended sediment in the water. And then we've got these black lines that show our salinity contours. So basically each of these lines represents a line of constant salinity. So here we've got about 1 PSU in this middle channel. In the historic case, when we have a shallow case, and then in the present day case, you can see that even during this ebb tide, the 1 PSU line is starting to propagate farther up estuary. And during flood tides, we see that that salt wedge, that landward limit of salty water is propagating several more kilometers up estuary than it used to. In terms of the sediment dynamics, now that we have this deeper channel and we have this greater propagation of salt, those are sort of ingredients to build up a zone within the navigation channel that is sort of perpetually more turbid than it used to be. So it's what we call an estuarine turbidity maximum. It's an area in the estuary where you tend to get a lot of sediment trapping, and it's just sort of perpetually muddy, both within the water column and on the bed. And that's really common in estuaries worldwide. That tends to happen. You have convergence of freshwater and saltwater, and sediment gets trapped there. It's just happening now in Coos Bay more than it used to, because there used to be a shallow channel where there were high current speeds and sediment could get flushed out. Now there's a deeper channel where sediment can really start to collect, and it sticks around a lot longer, and it likes to deposit there under that zone of high turbidity. We were also interested in what this meant as far as sediment trapping in the estuary. So we know that we have changes in how much sediment is in the water column, but we looked at the change between the historic and the present case and the proposed future case. We were interested in the effects on where does sediment get trapped and how much gets trapped. And this is just a bar graph that highlights the change in trapping between the historic case, which is blue, and the present case, which is orange. And we've subdivided it by different areas. So in the main navigation channel, or in the channel fallweg, there was actually a little bit of erosion in the model for the historic case. It was a very shallow channel, current speeds were very high. And in the modern case, you can see the dramatic effect of that channel deepening. We've basically created a nice sink for that sediment to settle in. And that's manifest through maintenance dredging that's done periodically to keep that channel open and clear of some of that sediment that keeps accumulating. On the east tidal flats and in the shallow embayments, we also see greater retention of sediment. And that has a bit more to do with changes in flood versus ebb tidal currents. So in some of these embayments, because of deepening in the main channel, that actually impacts the hydrodynamics in the shallower side embayments, even though they haven't necessarily been modified. And it just changes the balance of the tidal currents, and that also facilitates a little bit more sediment trapping. And this is an interesting result because we have a lot of questions surrounding estuaries worldwide in terms of how will they do under sea level rise, will marsh environments get submerged? And in Coos Bay, it seems like some of the modifications might actually allow these marsh surfaces to keep more sediment than they used to in the past, which suggests possibly good news for keeping pace with sea level rise. And with that, I'll pass it on to Jenni to talk about some of the stakeholder and end user engagement.
I think I'm going to talk about it too, actually. No worries. Thanks, Emily. Yeah, so from the outset, as Jenni was talking earlier, I think what made this project successful, besides the really great science that Emily was just showing, and that came out of our lab here at UO2 with the hydrodynamic model, was the strong engagement we had with the stakeholders down in the Coos Estuary. And a lot of this came about because of the partnership with Coastal Watersheds. This is a group that meets already every month, and it includes partners from nonprofit groups, government groups, for-profit groups, the Port of Coos Bay, all sorts of different stakeholders with different goals around the estuary. And so what we were able to do was in real time basically give them our results and hear their feedback. And it led to a lot of spontaneous requests for products like, oh, we're interested in this today. Like what, can you tell us something about the salinity levels in this part of the estuary, or averaged over this part of the estuary? And so we were able to deliver. This is a list of some example project deliverables. We're able to actually provide a lot of deliverables to that stakeholder group and our identified end users by the end of the project, and not just at the end of the project. Like here, this is our product, and just dump it on them. We're actually able to iterate with them and talk with them throughout the 3 years of the project. So that includes things like we made an exhibit panel for the local museum and aquarium in Charleston. We were able to look at deposition and erosion hotspots and overlay those with oyster or eelgrass habitats. And then the effect of the proposed dredging, that was a big issue down in Coos Bay. So all sorts of interesting deliverables that we were able to produce in this project, and mostly that was because of the stakeholder group that we had. Of course, it also led to lots of new questions, as I mentioned at the outset, and it also came up we were challenged a lot with how do we actually deliver on some of these stakeholder needs. At these meetings they would come up with these questions and they'd be like, well, it sounds like our project should be able to help with that, but actually we can't, or whatever it was. So all of that being said, what it did is it led us to a new collaborative science project where we're trying to respond to some of the questions and main needs that came out of this project. And so I think, again, it's just been a really nice relationship with the folks down in Coos Bay. So I'm going to spend about a couple minutes talking about this new project because I think it highlights some of the things we learned from this current project, and just to give you a sort of an ad for what we're going to next. So the new project is actually in particular looking at both oyster and eelgrass habitats in South Slough and the greater Coos Estuary. And in particular, we're thinking about sediment still. So how does sedimentation affect those habitats, or erosion? And then also, how does temperature variability affect both oyster and eelgrass habitat? And so on the left here, you can see some oyster habitats in the picture up here. And then we have this presence-absence map of oyster habitat throughout the estuary. And you can see that South Slough, despite the oyster restoration efforts going on, it still has an absence of oysters. There's an absence in main channel, but then there's lots of oysters on the East Bay. And this is the native oyster, Olympia oyster, that we're talking about here, which has a lot of interest right now. And then, of course, eelgrass is another story. And this is a picture of eelgrass in 2002, and then in 2018, after the big decline, at least within one site at South Slough, which is this Bellino Island site. This is the mean shoot density of eelgrass over time. And if you just look at the light green dots, which have the most samples sampled every quarter, you can see this sort of die off through 2015, 2016, into 2017, and it still hasn't really recovered. But that die off isn't uniform across the estuary. And so I think we're able to use this sort of as a natural laboratory to ask some questions about what's causing die off in eelgrass and what's causing the presence or absence or success of oyster restoration. And so to do that, we're doing a bunch of things that are building off of this current project that we just talked about. So we're continuing some time series analysis of the swamp stations. And so this map over here actually shows you the water quality stations, both in South Slough, these red dots, and then also within the Coos Estuary, we have some sites that we're able to get data from. We're going to add water temperature as a variable into the hydrodynamic model. So right now, all we model is water elevation and salinity, which are the main drivers of estuarine dynamics. But if you want to start thinking about temperature effects on eelgrass or other biology or ecology questions in the estuary, it's really important to have temperature. And then we're going to be collecting some new sediment cores around existing eelgrass and habitat and oyster beds to think about the short-term, like seasonal to longer-term history of sedimentation in those areas, to think if we can answer some of those questions about what makes an area successful or not. And then, of course, we have a lot of end users, some the same as this current project and some new ones. We've really benefited from collaboration with the tribes, and then also with Coos County as they sort of update their estuarine management plan for the Coos Estuary. So just a quick summary and some lessons learned. I think, hopefully it was clear through this project that we had really early in user engagement, and that came through the Partnership for Coastal Watersheds group, and then also just the really regular meetings that we had. So I'd say that, the lesson that we learned was just often meetings with the end users just pays off in the end. You're not left with giving them a report at the end of the project that they throw in the trash. I also think it's important to note that we built some really basic science tools, right? So there was a lot of upfront effort to build this hydrodynamic model and then the sediment model, but now we have this working model that we can use to answer some questions. And it's not as big of a push to add temperature to the model as it would be to build the whole model again. And so we can use that tool now to answer some applied science questions that, maybe ODF&W has, the Fish and Wildlife, or the Department of Environmental Quality, or the tribes, or whoever it is that come to us with questions. We can try to help answer them. Of course, some difficulties remain, and sometimes that's the science translation. So that's this mismatch between our model output and what we can actually answer, or the analyses that we're doing with the model or the observations that we have, and what the answers that the stakeholders and users want from their questions. And sometimes that's a timescale mismatch. They might want something about sediment, dynamics over decades to centuries, like what's going to happen with sea level rise. And we can't directly answer that with our model right now, but we can certainly hint at some of the answers to that question. Or it could be a very local, very spatially local question that we can't quite answer, like, oh, what happens in this 1 meter square part of the estuary that our model just can't resolve. And so we do still have some difficulties with trying to translate our science between the applied questions and what we can actually do. And then I'd say just another lesson learned is not to overpromise from the beginning and just sort of lower your expectations. And because it's not the it's not the end all be all, this one project. So there's going to be other projects, and you can, I think, trying to work on some quality part and not quantity is pretty important. And that's it. I'd say please get in touch if you have questions. So our emails are up here, or get in touch with anybody else listed on the sheet up there. And I posted the project page at the bottom again for some of the papers and other products that we've generated. But I appreciate your time, and I guess we'll be happy to answer questions. So thank you. Pass it back to Nick.
All right. Thank you, Dave. Yeah, we'll go ahead and invite all of our presenters to come off mute and back on camera as well. We have a few questions that came in during the presentation, so we can start with those. You can see Megan and I kind of typing them in here. But so somebody had a question about the model. For the upstream of Coos River inside the model domain, what is the source for the bathymetry?
Yeah, that's a good question. The jet skis were able to get fairly far up the Coos River channel. And actually there's some really neat, like, deep pools and deep holes in that. But then, we actually extend the model domain all the way to the head of tide in order to, or we try to, as far as we can, and put our river inputs at those nodes in the model. And for that, we basically just set a constant depth and didn't try to mimic what the real bathymetry or topography would be. And that's often in models, I'd say that's often what you have to do. It's a little bit of an art, a little bit of science. And so you don't want to believe anything too close to model boundaries, I guess, is the thing. So the freshwater inputs coming in, we believe it when it gets into the estuary and how it interacts with the salt there. But anything up too close to the estuary, to the river inputs, or to the offshore ocean boundaries, I'd say are not to be believed, if that answers your question.
Other presenters, you can also feel free to respond and build off of answers if you want to. Somebody also put in a comment that just says excellent presentation, so I just thought I'd pass that on to you while you're all here.
Thank you.
Very thorough. I know that there are a few questions that were answered while you were like towards the end of the presentation. There was questions that rolled in that Megan, I think, just moved because she said, oh, never mind, he answered that. So very thorough presentation. Just encourage everybody, don't be shy, just type your questions in and Megan or I will read them off. So the next question, was the salinity concluded using sediment inputs or outputs from the model?
Can you repeat that again? Was the salinity?
Sure. Was the salinity concluded using sediment inputs or outputs from the model?
I'm not sure.
Does that perhaps mean, or does the question ask if the salinity was related to the sediment dynamics?
Yeah.
Because yes, that definitely was the case. Where it's in fact, that's a really important part of sort of estuarine dynamics and estuarine sediment transport, that including the effects of salinity on the circulation patterns, on the stratification, on how it affects the turbulence and resuspension of sediment is really important. And I think Emily did a really nice job of highlighting how the changes in bathymetry, which then change the salinity distribution, then have a big impact on where the sediment ends up.
Yeah. Thanks, Dave.
Ooh, lots of questions rolling in. All right. Let's see if we can get through all of them before time is up. Okay, so next question. I know this is beyond the scope of the project, but I'm curious if you had a chance to look into how historical changes in the estuary have affected the hydrodynamics, thinking about the plume as always, and sediment dynamics of the coastal ocean in the region.
Yeah, we didn't try to look outside of the estuary mouth at all, I'd say. And that was a little bit by design because we didn't include time variable boundary conditions on the ocean side. And so we weren't actually trying to simulate what was happening out in the coastal ocean. But what I can say, and maybe Emily can add to this, is that we did look at the changes in the hydrodynamics between the historic and present day case. And we only talked very briefly about it here, but it's highlighted somewhat in her paper. And there's changes to the tidal regime, there's changes to the stratification, like Dave just mentioned, and to the ebb dominance of the tidal currents themselves. So we definitely looked at what happens to hydrodynamics inside the estuary, but yeah, sorry, I can't say any more about what happened outside the estuary. That would be fun though. Yeah.
Okay, no anything else to add to that one. I will move on to the next question here. Okay, so one difference between the historic and present conditions is the amount of diking that has happened in the Coos River. How does that influence sediment flow?
Do you want to answer that one, Emily, or?
Sure. I'm sorry, Nick. Can you repeat the question?
Sure. One difference between the historic and present conditions is the amount of diking that has happened in the Coos River. How does that influence sediment flow?
Thanks. My Google kicked me off the question sheet. That's a really interesting question. I think that presumably that would impose some limitation on how much sediment is getting into the bay to some extent, because some of those sediments might be trapped behind the dikes. We've certainly heard of other studies where that has happened. But if you assume that the majority source of sediment to the estuary is being flushed from steep hill slopes farther upriver, then I think there could be a secondary effect of how those dikes impact circulation within the estuary. And there have been other studies related to that where you can get some local intensification of circulation near the dikes, and you can actually get sediment piling up on the seaward side of those dikes. So that's an interesting idea, and perhaps that's something you could answer by going into those diked areas and collecting sediment cores to see how accumulation rates there have changed.
Yeah, I will mention that. That also reminds me that there's some parts of this estuary are behind tidal gates as well, and we're not modeling that in the model right now, so we're not including that sort of one-way flow. So there's some things we couldn't answer when our stakeholders had questions about tidal gates in particular. We just kind of said sorry.
Got about 10 minutes left. We're making good time here. A few more questions to answer. Were you able to model erosion of mudflats?
So the mudflats are an interesting question because they are such a big part of the estuary, and to some extent, yes. We played around, we put a couple different sediment classes in the model. We actually seeded the model with a highly erodible bed and let it run for a few months to try to sort of establish itself and self-segregate sediment sizes. The one limitation of the model is that it's not really resolving processes happening when the water depth is less than about 40 centimeters. So that is a little bit of a limitation, but when the water depth is greater than that, we're certainly modeling what's happening with the turbulence on those flats and seeing how sediment is being eroded and deposited.
Yeah, just to expand on that, I mean, taking full blame for the model setup, we didn't necessarily model every process that happens in the estuary and on the tidal flats. And for example, it's quite likely that the influence of wind waves is particularly important there. We didn't directly model the influence of wind waves. And so that's certainly kind of an open science question, the extent to which that is a key limiting factor on the accumulation of fine sediment. I think we have a good sense of sort of what the changes in bathymetry and how the river and the estuary is delivering sediment to the tidal flats right now. And I guess the question is the extent to which sort of that when you have shallow water with a lot of fetch, that wind waves then create bed stresses sufficient to then either move it more landward or move it back offshore into the deeper tidal channels.
Thank you, Dave. Okay, so somebody wants to know what kind of expertise it takes to run this model.
That's a good question. Yeah, so the model is called the finite volume coastal ocean model. It's an open source model. So it doesn't take any getting the model code itself and doesn't take any particular expertise other than being able to find it online. But then the biggest thing is having the computational power, I'd say, to run the model. So two things. One, computational, requirements. So we ran this on a UO's, University of Oregon's cluster supercomputer because it takes a lot of computing power to run this model. And then also, I'd say it takes some knowledge of estuarine dynamics to run it, at least run it correctly, because you want to make sure that whatever output you get, the model's only as good as what you put into it, and you want to check how reasonable it is when it comes out. So someone could go run this model, but then if you don't know anything about estuaries, it might be really difficult for you to say what's actually happening. So some of it's computational, computer science sort of expertise, and some of it is more like oceanographic marine science expertise, and it's a melding of those two. It's not a black box like hit a button, run a model. It's much more, it's like any other open source code. You sort of have to know a little bit about what's going on behind the hood, under the hood.
So it's a bit of a follow-up question to that. Could non-expert natural resource managers run it themselves for specific questions? It sounds like you started to answer that.
Yeah.
You might need help with a supercomputer, but.
Yeah, probably not. But there's things, that's where that science translation question comes in for us. And we were working a lot with, folks from the Coos Watershed who were interested in salinity levels, salinity thresholds for salmon in the estuary, or ODF&W wanted to know, in this area, what's the daily mean or the monthly mean salinity or temperature over a certain, season. And those are the fields. We can actually generate data or even GIS maps of those sorts of products and just give them to you. Running the model is a little bit more involved, and I'd say it's probably not feasible for us just to give it to somebody and let them run it without some prior knowledge.
Got about 5 minutes left, so we're going to see if we can get a few more questions answered here.
Yeah.
So as most of our estuaries are undergoing nav channel deepening, widening, required to support the local ports, what is your takeaway for impacts and how to avoid or minimize them?
Yeah, I don't know. Emily, do you want to maybe summarize what the impacts were, and I can think about
Yeah, I think that the impacts we see are common to a lot of estuaries, where you're basically creating what we call accommodation space. You're creating space to accommodate the deposition of sediment and trapping of sediment, which then necessitates more maintenance dredging. So it's an interesting question, because I think in the eastern part of the channel, we've certainly seen that dredging create a space where sediment is now accumulating, where you're forming a stronger ETM that persists and facilitates deposition. On the western channel, when the estuary gets deepened, that causes a little bit of reduction in tidal currents, but we saw an interesting effect where on the western channel, it's actually becoming a little bit more ebb dominant. So on the one hand, you might have potential to trap sediments there more readily, but also the net migration of the sediments might be more seaward. So it would be really fascinating to run the model over a longer simulation to see how those effects aggregate over several years. But at this point, I think just our general understanding of dredging and deepening in estuaries is that you create a potential to retain more sediment in those channels.
And yeah, I'll just add on, Dave, sorry, but in most of these new projects in estuaries, if they're building something new in one part of the estuary, then they're probably going to have to mitigate that and make some restoration project or mitigation project somewhere else in the estuary. And I think that's the important question: is how well do those mitigation issues or plots work, and often they don't work well at all. And so I think if you're going to, harm or impact one part of the estuary, you want to make sure that those mitigation and restoration efforts are actually successful. And so putting more focus on that part is probably important. I'm sorry to interrupt you, Dave, but.
I know, sorry, that's great. I was just going to expand on what Emily said. I think so. Emily's background's in geology and sediment, but there's also a lot of physical oceanography that changes, which is really important. And I think, I mean, she has a really nice paper on sort of the changes in the tides. Basically, the tides get bigger because it's deeper. There's less frictional, so the tide can move into the estuary and stay big easier. And there's also all the changes to the salinity distribution, basically how far into the estuary the salt gets, how stratified it is. And so those have all sorts of ecological implications and potentially human use implications too. For example, drinking water intakes or so forth, or for that matter, with the change in the tide, the changes in tide are a lot bigger than changes in sea level in some cases with global sea level rise. And so I think this study was a really nice example of sort of, by having good documented historical data and also this modern condition of sort of really going through and detailing, well, here's what happens when you make a deeper estuary. And I think it applies to this system, the Coos Bay system, but it also is a really nice example that can be transferred to other systems. And that's, a nice paper came out of that.
Thank you all. We've got time for one more question here, so I'll just pose this final question. Can you comment on the expected difference in sediment dynamics that may occur in response to continued maintenance dredging versus major deepening and widening of the primary tidal channel?
I think that's a fairly complicated thing to try to predict. I would guess that they're probably going to need to do continued maintenance dredging just because the estuary is going to continue trying to fill up some of those channels, especially the upper channel, and return to a more natural configuration. And again, as far as the deepening and widening of the primary tidal channel, we talked about that a little bit in response to the last question, but there's evidence to suggest that you might get a little bit more sediment accumulation, but as Dave just noted, there are a lot of interrelated hydrodynamic effects occurring too. So you do expect an increase in your tidal amplitudes. There's going to be a change in whether your ebb tides or your flood tides are a little bit stronger. And we do see it becoming a little bit more ebb dominant. So it's a little tough to predict. It seems like something where we'd want to run model simulations for a longer period of time to really get at some of those questions.
I guess I would also just add the caveat that the hardest part about the historic case and making predictions in the future is also the sediment input to the estuary. And that's something that we, you just have to sort of make our best estimate of. We don't know what the sediment input was. We're just assuming it's similar scaled to the discharge than it is at present day. But if there's a lot of landscape change in the watershed, then that can change what the sediment input is into the estuary itself. So I guess we're out of time though.
We are about out of time. If you didn't get your question answered, don't worry, we'll try to get it answered in the next couple of days and add it to the summary product. Thank you to everyone who asked questions. Thank you to our presenters for presenting and also for answering questions for us as well. It really does help, and we love having them around to answer the questions. And thank you for putting together such an excellent and thorough presentation. I, for one, found the videos super informative. Very cool to add those in for those of us who like alternate styles of seeing information. So our next webinar is scheduled for November 30th. There's not a whole lot to share about that one just yet, but stay tuned. If you want to follow those announcements, you can sign up for webinar announcements and or program updates through our mailing list. So you'll see there's a little link in the exit survey that'll be released after you end the session and also tomorrow around the same time that the webinar started today. So you'll receive a follow-up email from us basically, and it'll have the exit survey, which please take it. It really helps us kind of determine what works and what doesn't for the series. So I do read the comments and everything that are in there. So if you have stuff to share, please share it there. And again, there'll also be a link to the summary resource product. So stay tuned in the next couple, I don't know, a week or so, next couple days for responses to those questions as well. So again, we'll just end with another big thank you to our presenters for taking the time to be with us today and for putting together a great presentation. And everyone have a great day.
Thank you.